All right. Good morning, everybody. So that will be our last week of classes, and next week on Tuesday, you will have your final exam. Okay. Um, so for this week, we will have to cover uh, the chapter number 9 and chapter number 10, and probably part of chapter number 11 as well. So let's see if we can accomplish all of that. Um, to start the class today, some quick announcements here. Do not forget that you have online homework for chapters number 9 on due on Monday. So this is already available, and you will also have an online homework for chapter number 10 that I will post uh, today or tomorrow on SmartWorks. Those homeworks are going to be very short, and you should not have any problems solving it. I believe you also received an email about the course evaluations. So please do not forget to complete the course evaluations for the lecture, the discussion, and the lab for CHEM 109. If you think the course was good, write there. If you think it was not good, write there what you think was not good and what could be changed, and then we can change for next semester. Okay, with that being said, let's move on. The topic for today is molecular geometry, okay? And that's going to be chapter number 9. We will cover Vesper and polarity of molecules. However, unfortunately, we will not have time to talk about valence bond theory, neither molecular orbital theory, unfortunately. If you wanna read about it, it's going to be chapter 9.4 and 9.6. Okay. All right. With that being said, so let's move on to molecular geometry. Okay, biological processes they are based in the interaction between molecules and proteins. In this case, shape and charge distribution play important roles. Okay, and that's one of the reasons why sugar has a sweet taste, and how can we create compounds that taste similar to sugar. Another observation is that CO2 is less soluble in water than SO2. Okay? Both compounds have one central atom bonded to two oxygens. However, one of them is not so soluble in water, while the other one is freely soluble in water. What's the reason for that? And another thing that molecular geometry plays an important role is in the chemical process behind vision. Okay, what what's happening uh, chemically speaking when we see objects? So that's our goal for today. So we have to start from the basics. So let's do here a quick recap about Lewis structures and formal charge. Remember, for a Lewis structure, we are going to figure out how the atoms are connected. So we can start using the Clark's rule to have an idea about the structure. Careful, because there are few exceptions for the Clark's rule. Second step is to count the total number of valence electrons. Don't forget to account for charges. If there is a net negative charge, you have to add electrons. If there is a positive net charge, you have to remove electrons. The fourth step is to choose the central atom. The central atom is usually the largest element in the formula, okay? Usually the element in the lowest number and the less polar one. And once everything was done, now distribute the electrons among the atoms to fill the octet. Do not forget, if you have an atom from the third period or below that, the octet can be expanded by using d orbitals. To confirm that the Lewis structure that you got is correct, you must calculate the formal charge for every atom in the structure. Ideally, the formal charge has to be the lowest one on the atoms in the structure. Always avoid double or triple charges on the atoms. And if there is a negative charge, that charge has to be located at the most electronegative atom. For example, here, the structure of the nitrate ion has a nitrogen in the center of the structure, single bonded to two oxygens and double bonded to one of the oxygens. And that's the structure that provides the lowest formal charges for the atoms. Although there is a charge different from zero in the oxygen and nitrogen, it is correctly assigned as a negative charge to the oxygen and a positive charge to the nitrogen, because oxygen is more electronegative than nitrogen. Okay? Build a Lewis structure is going to be the first step in determining the correct molecular geometry. Okay, if that step fails, it's going to be a domino effect, and your molecular geometry will be wrongly assigned. Okay, so to start, let's ask you a question. How are the atoms for the CO2 molecule organized in space? So damn it. Let's draw here some options, and then we will analyze every option and figure out which one will be the best. Okay, so CO2 has a carbon as a central atom, and this carbon is double bonded to the oxygen. So I'm going to draw a first hypothesis here. I can draw slightly different. Okay, so I'm increasing the distance between the oxygens. Then let's draw a third option over here. And finally, a fourth option. Okay, so all the atoms really spread out. Okay, this I'm going to call number one, number two, number three, and number four. Okay, so drawing the Lewis structure will not tell us anything about the shape of the molecule. Lewis structure only tells us how the electrons are being shared. So if I would ask you just to use your chemical knowledge, which of the four structures would you think is the most stable? Let's think about that for a couple minutes, and then we will analyze which is the most stable. Okay, so remember that a covalent bond is basically electrons being shared, and we also have electrons around each element. Therefore, closer the atoms are, higher is the repulsion between the electrons. Okay, so the structure number one has oxygen really close to the other oxygen. And remember that we have lone pairs here. So the repulsion between these two atoms is going to be so high that this structure is not stable at all. In the second possibility, they are a little further, but still uh, considerably uh, close to each other. So let's start moving one oxygen further apart. So in the situation number three, it's much better. However, the option number four is the option that has the oxygen atoms further apart. And that's the idea when we do molecular geometry. The system will acquire a 3D configuration in order to minimize the repulsion. Okay, so the key word in molecular geometry is to minimize repulsion. Okay, so we will acquire a configuration to minimize the repulsion. And that's the Vesper model. Any system tends to adopt a spatial configuration that decreases the repulsion between electrons. Okay? If the angle between two groups is 90 degrees. That's one of the highest repulsions possible. 120 is a little bit less, and 180 is the lowest repulsion possible. Okay, so 90 degrees is less stable than 120. That's less stable than 180. We will come back to this later on today, but the repulsion between lone pairs or non-bonding pairs is higher than the repulsion between a lone pair and a bonding pair. That's higher than the repulsion between bonding pair and bonding pair. Okay? What that tells us is that lone pairs, they have to be as further as possible in the structure. Okay? They will repel everything with the highest intensity. All right, guidelines to get the molecular geometry. Let me change to the other screen. Okay, so we have two different things that are connected. The first one is called electron pair geometry, and that is the relative position in the space for all the bonding and non-bonding pairs around the central atom. So we always start with the electron pair geometry, and for that, we will consider everything that's around the central atom, okay? After we determine the electron pair geometry, then we are going to determine the molecular geometry. For the molecular geometry is the relative position of all the bonding pairs around the central atom. Okay? See the difference? Electron pair geometry will consider bonding and non-bonding pairs around the central atom, while the molecular geometry will look at only the bonding pairs. First step is to determine the electron pair geometry. For that, we will first determine the steric number and then organize the bonding and non-bonding pairs around the central atom to minimize the repulsion. To determine the steric number around the central atom, if there is a lone pair, we will consider as 1. Single bond we will consider as 1, double bond 1, and triple bond 1. The steric number is going to be the sum of everything that's around the central atom. Okay, so let's do here two examples. First one for the nitrate and the second one for the water geometry. The goal here is first to determine the steric number around the central atom. Okay, so let's start with the nitrate. For the nitrate, I'm looking at the steric number for the nitrogen, because that's the central atom. To determine the steric number, we are going to count bonding and non-bonding pairs, and we will assign numbers to each of them. In this case, we have two single bonds. Each single bond is 1. So far we have 1 plus 1. And we have a double bond, which is assigned as 1 as well. Okay? Therefore, the total steric number around the nitrogen is going to be 1 plus 1 plus 1, which will give a steric number equals to 3. Okay? So for the steric number, just add up everything that's around the central atom. Lone pair is 1, single bond is 1, double bond is 1, and triple bond is 1 as well. Now, let's take a look at the water molecule, and let's calculate the steric number for the oxygen. Okay. Attention now that the central atom is oxygen, and that's the one we want to determine the steric number. So let's see everything that is around the oxygen. We have two single bonds with the hydrogens. Each single bond is 1. So far we have 1 plus 1. And in this case, we also have two lone pairs, okay? Each lone pair accounts for 1, and we have 2, therefore it's going to be 1 plus 1, which will give us a steric number around the oxygen equals to 4. Okay, see the difference when you have lone pairs, you also have to count them because the lone pairs will repel the atoms and will contribute for the molecular geometry. Once we have the steric number, now the next step is to organize the bonds and the lone pairs in the space to minimize the repulsion. And that's our second step. Okay. Now we are going to arrange the bonding and non-bonding pairs to decrease repulsion. If we have steric number equals to 2, the most stable way to arrange that is in a linear fashion. Okay. In this case, the repulsion is the lowest possible. For steric number equals to 3, the best way is to organize in a trigonal planar fashion. Steric number equals to 4, it's going to be tetrahedral. Steric number equals to 5, we must organize as a trigonal bipyramidal fashion. For steric number equals to 6, octahedral. Steric number equals to 7, pentagonal bipyramidal. And steric number equals to 8 is not very common, but the organization will be a square anti-prismatic. Okay. Okay. To help us to visualize the 3D shape of each of these organizations, we can use solid bonds and dashed bonds. So let's do here for the tetrahedral. So you will draw that in this way. So we have the central atom here, the green one. The bond upright is in the same plane. So we draw a normal bond like that. However, the bond between the central atom and this atom over here is coming out of the screen. So the way to represent that is to draw this way, okay? Coming out of the screen. The bond between the central atom and the atom on the right side is going towards the screen. So we are going to do like dashed, okay? And the bond between the central atom and the atom on the left is going towards the screen as well. So we draw like that. Let me draw this better. And that will give us a better idea about the 3D shapes. Okay. Using solid bonds, dashed bonds, or that kind of bold bond here. Okay, so that's the representation used to better visualize a 3D structure and the organization in the space. Okay, so you need to know this, okay? At least 2, 3, 4, 5, 6, and 7. I would say 2, 3, 4, 5, and 6. Those are the most common cases. Sometimes you can have 7 and not usually a steric number equals to 8. Remember that the steric number will give you an idea how the bonding and non-bonding pairs are organized in the space. And that's called electron pair geometry. Okay, and then finally, the last step is to place the ligand atoms in the designated positions, and that will give us the molecular geometry. Okay, with that being said, let's do a practice here. So let's determine the electron pair and the molecular geometry for three different compounds. First one is CO2, second one is nitrate, and third one is PCl5. Okay, so what I usually like to do is to organize this in a table where the first column is going to be the molecule. So for example, here CO2, and then the second column is going to be the steric number. The third column, we are going to determine the electron pair geometry, okay, the name of the electron pair geometry, then molecular geometry, and then here in the last column, we will draw uh, the molecular geometry, how the atoms are organized in the space. Okay, so let's do that for CO2, nitrate, and PCl5. When you are determining the molecular geometry, I find this table here on your right side very, very useful. So let's try to use that. Okay, in this table, we have steric number on the vertical, and then the geometry uh, for the steric numbers in the first column. So let's think about that for a couple minutes, and then I will start uh, solving the problem with you. Okay, so let's start with the CO2. For CO2, we know that the Lewis structure has carbon as a central atom, and that's bonded to the oxygens through two double bonds. Okay, and there is no lone pair on the central atom, only in the bonding oxygens. Okay, so remember that we are looking at the molecular geometry for the central atom, and that's going to be our focus. First step is to determine the steric number. For the steric number, lone pair, single bonds, double bonds, and triple bonds, they will count as one, and we have to add everything that's around the central atom. For carbon, we have two double bonds, therefore steric number is going to be 1 plus 1, which is equals to 2. Okay? For the steric number equals to 2, now we will go to the table and find here that steric number equals to 2. The most stable arrangement is linear. Okay? So we have carbon and then a linear arrangement. Now, for the molecular geometry, we are going to fill up the spots available with the bonding atoms. In this case, we have a linear arrangement, and we are going to fill this linear arrangement with the oxygens. And for the molecular geometry, you will only look at the bonding atoms. Okay? In this case, there is no difference between the electron pair geometry and the molecular geometry. Therefore, we have molecular geometry as a linear, which means the most stable arrangement for the CO2 molecule is that is a linear shaped molecule. And it will be something similar to that. Okay, carbon in the center, oxygen on the left, and oxygen on the right side. Okay, so now let's move on to nitrate. Lewis structure for nitrate. We have a double bond at the top, two single bonds on the left and on the right. Okay, so again, we are interested in the central atom, so we are going to look at the central atom. We already determined the steric number for nitrate. It's going to be 1 plus 1 for the single bonds, plus 1 for the double bonds, which gives us a steric number equals to 3. Okay, so we are looking at everything around the nitrate. 2 single bonds, 1 double bond. Therefore, the electron pair geometry, according to the table over here, it's going to be trigonal planar. Okay, so nitrogen will organize everything around it in a trigonal planar fashion. For the molecular geometry, now we are going to fill up the spots available with the ligand atoms and then look at only the bonding atoms. In this case, there is only 3 spots available, so we are going to fill it with the oxygens. And therefore, the molecular geometry is going to be the same as the electron pair geometry. Therefore, the nitrate is a trigonal planar molecule. And the spatial arrangement will be something like that. Okay, so one group on the top, one on the left, one on the right. This is a triangle with the three sides as the same length. Therefore, the angle between each bond is the same and equals to 120 degrees. So steric number equals to 3. Trigonal planar geometry is the geometry that will decrease the repulsion. And finally, PCl5. PCl5, we have here an example of octet expansion for the central atom. Okay. Phosphorus is bonded to 5 chlorines, and we are interested in determining the molecular geometry for the central atom. So let's start with the determination of the steric number. We have here 5 single bonds, therefore 1 plus 1 plus 1 plus 1 equals to 5. Go to the table, see for steric number equals to 5, what is the most stable geometry? Right here, according to the table, is going to be trigonal by pyramid. Okay, so phosphorus at the center of the structure. So we are going to have something like that. Okay, phosphorus here at the center, and then we have a couple of bonds in the vertical axis, one bond here in the same plane, another bond going out of the screen, and a fifth bond going towards the screen. Okay, see here, we have these 3 bonds in the same plane. This one, oops, this one coming out of the plane, and this one over here in the back going towards the plane. So how can we draw that in a good way? I like to do that. The vertical bonds, they are in the same plane, and one of the bonds in the plane is also in the same plane. One of the bonds is coming out, so that's how we draw it. And another one is towards the screen. And that's how you represent a trigonal bipyramid. For the molecular geometry, we fill up the spots with the bonding atoms. Therefore, we have 5 atoms to fill up. So we are going to fill up all the positions available. And in this case, because there is no lone pair at the central atom, the molecular geometry is going to be the same as the electron pair geometry. Trigonal by pyramid. Angles in this structure. Okay, the angle between the bond pointing towards the top and the plane is 90 degrees, and the angle between the bonds in the plane is 120 degrees. Okay, and that's the shape we are looking for right here. Okay, so determination of molecular geometry is simple. It's not hard. However, you have to make sure you have the correct Lewis structure. Okay, everything starts from there. If you make a mistake, it will carry over and you will end up with the wrong molecular geometry. So right now, we are capable of determining the 3D shape of any molecule possible. Okay? The shape of the molecule is the one that will have the lowest repulsion possible. Remember, any chemical system tends towards the lower energy, the lowest energy possible. And organizing the atoms in a 3D fashion will move towards this goal. Okay, all the examples that I showed you so far do not have any non-bonding pairs in the central atom. So what happens when we have a one or more non-bonding pairs in the central atom? So let's take a look at the electron pair and the molecular geometry for water. Okay, so the same idea here. We are going to build a table with molecule, steric number, then we are going to determine the electron pair geometry, and after that we are going to determine the molecular geometry. So we are dealing here with water. We know that in the case of the water we have oxygen as a central atom bonded to two hydrogens, and attention here, we have two non-bonding pairs for the oxygen. First step is the determination of the steric number. So we are going to look at the central atom and count everything that's around the central atom. We have two single bonds. Each single bond is one. And we have two non-bonding pairs. So we have to add that as well. That will give us steric number equals to 4. Go back to the table. Let's look for steric number equals to 4, which is the best way to organize these 4 groups in the space. According to the table, tetrahedral way is the best one. Therefore, the electron pair geometry is going to be tetrahedral. Okay, so oxygen in the center, we have one group up and then 3 groups down. So that's how the groups are going to be arranged around the oxygen. Okay, so tetrahedral, something like that. Now, be careful, because the molecular geometry is going to be slightly different from the electron pair, because we only have 2 atoms bonded to the central atom. Okay? So what I'm going to do now is, from the electron pair geometry, I'm going to place the hydrogens in any position because all the positions are equivalent, and then the electron pairs in the positions that are left. So that's the electron pair geometry. When you look for the molecular geometry, you are going to ignore the electron pairs in the drawing and only consider the atoms that are bonded. Okay? So we had this geometry as the electron pair geometry. However, we only have two atoms bonded. So we are going to place the two atoms in a random position because all the positions are equivalent. Okay, so two positions are occupied with hydrogen and the electron pairs are in the two positions that are left. For the molecular geometry, we are going to ignore the non-bonding pairs and only look at the atoms that are bonded to the central atom. Therefore, that's the geometry that you have for the water molecule. Okay, so this geometry is called V-shaped or also called bent. See the difference between electron pair geometry and molecular geometry when you have lone pairs in this at the central atom. So be very, very careful to don't get this wrong, okay? It has to be clear the difference between electron pair geometry and molecular geometry. Electron pair, you will consider everything. Molecular geometry, you will fill the positions, hide the non-bonding pairs, and then only analyze what is bonded to the central atom. All right, very good. So now that we know that some cases the electron pair geometry can be different from the molecular geometry, we can expand the table. Okay, so now we have here still steric number around the central atom and then the number of lone pairs for the central atom and all the possible geometries. For water, we had steric number equals to 4 and 2 lone pairs. Therefore, the molecular geometry is called bent or also V-shaped. And here the angle between the two hydrogens is around 109 degrees, which is the same angle between the OH bond and the lone pairs. Okay. So again, it is crucial that you get the right Lewis structure, and then from there is not hard. Determine the steric number, choose the correct electron pair geometry, and then the correct molecular geometry. And with that, you will be capable to tell what is the 3D configuration of any molecule. Okay, so now that we know all the possibilities, let's do one more example for the SF4. Okay, what I would like you to do is to determine the electron pair geometry and then the molecular geometry. You can use the table, okay? So that will make your life easier. Remember, first step is to come up with the right Lewis structure, steric number, electron pair geometry, and then molecular geometry. Okay, so let's give you a couple minutes, and then I will start solving it.
Professor?
Okay, so let's start solving this problem for the SF4 molecule. First thing is to determine the correct Lewis structure. SF4 is an example of octet expansion. So we are going to have here 4 atoms of fluorine bonded to the sulfur. All the fluorine have the octet field, and then there will be one lone pair, one non-bonding pair that's going to go to the sulfur. Okay, so in this case, sulfur has 10 electrons in the valence shell. Okay? That can be achieved by expanding the octet and using the d orbitals. Okay, so again, the Lewis structure will not tell us anything about the organization in the space. To do that, the first step is to determine the steric number for the central atom. So we are looking here at the central atom. So let's start with the determination of the steric number. And that's going to be 1 plus 1 plus 1 plus 1 for each single bond. Okay, so 1, 2, 3, and 4. And in this case, we have to add also the non-bonding pair right over here, which gives us steric number equals to 5. For steric number equals to 5, what's the most stable geometry? What's the most stable electron pair geometry? Go back to the table for steric number equals to 5, which will be the most stable geometry. If you go back there, that's going to tell you that is trigonal by pyramid. Okay, so sulfur is going to organize all the bonding and non-bonding pairs in a trigonal bipyramid fashion around it. Okay, so we have 2 bonds here in the vertical, 1 bond in the same plane, another bond coming out of the screen, and then the final bond coming towards the screen. To draw that in the correct way, so let's do 1, 2, 3, the 4th coming out, and the 5th coming in. Oops. Okay, so now that we have the electron pair geometry, the next step is to determine the molecular geometry. Again, you can use the table. In this case, we have steric number equals to 5. However, we have one non-bonding pair, one lone pair. Therefore, the most stable molecular geometry is the one that has fluorine, fluorine, another fluorine over here, and another one over here, okay? So we have the non-bonding pair right in this position here. For the molecular geometry, you just ignore the non-bonding pair and look at only the atoms that are being bonded to the central atom. So we have one fluorine over here, another one over here. So that's how it is. One fluorine coming out of the screen right here, and the last one going towards the screen. And that would be the molecular geometry. Okay, so something like that. And this geometry is called seesaw. So the question I want you to think about for this case, why the non-bonding pair is in this position and not in this position over here. Okay, so why we have the lone pair in the plane and not pointing up? You don't need to answer me now, but think about that. Okay, so now that we are capable of drawing any molecular geometry, let's talk about uh, polarity. Okay, so we know that CO2 is less soluble in water than SO2. And what's the reason for that? So for water, we know that this is a polar compound. Therefore, it will have preference to solubilize polar compounds instead non-polar compounds. The CO2 has a linear molecular geometry. The bond carbon-oxygen is polar. However, they point in opposite directions. Therefore, the sum of all the vectors in this compound will yield a resulting dipole moment vector equals to 0. Therefore, this is a nonpolar compound, which yields low solubility in water. What's the difference when we move on to SO2? SO2 now has a non-bonding pair at the sulfur, and that will change everything. Now for SO2, we have a bent molecular geometry. So now the oxygen atoms are not in the same direction. So we bent the molecule because of the presence of this non-bonding pair. Again, the bonds between sulfur and oxygen are polar. And in the case of the SO2, the sum of all the vectors will yield a resulting dipole moment vector different from zero. If the sum of all the vectors is different from zero, this compound now is polar. And that's why SO2 is more soluble in water than CO2. Okay? The shape of the molecule will change everything. And we need to be capable of determining the correct geometry. Okay, so let me go back to the PowerPoint. All right, so now we can answer some of the questions that I asked you in the beginning. Uh, First, the sweet taste for sugar. So sugar has the right size and charge distribution to interact with taste receptors in our tongues. And this interaction causes stimulation of electric pulses that will give you the sweet taste sensation. Okay, so the molecule has the right size and charge distribution to interact with these receptors. And that's the basis to design artificial sweeteners. We have to design something that interacts with taste receptors in the same way sugar does. Okay? So emulating the nature in the lab. Sometimes the interaction is so strong between the sweetener and your taste receptors that it seems like the sweetener is sweeter than sugar. Okay, so stronger interaction will give you this sensation. And here, what's the chemical process behind vision? In your eyes, you have a compound called retinol, and this compound, looking at the configuration of this double bond here, can have the cis configuration or the trans configuration, and this change is caused by light. Once the light is removed, the compound will go back to cis retinol. The frequency in which the cis form is transformed to the trans form will create electric signals that will be read by the brain and create the image. Okay? Therefore, changing in shapes will cause electric pulses that the brain will read and build the image. And again, shape being involved here. Okay, so the Vesper model is very, very useful and very good to explain molecular geometry. However, it does not explain how the bonds are formed. So we started with the Lewis model that shows you how electrons are shared. The Vesper model will tell you the configuration in the space of the molecule. And then with the valence bond theory and the molecular orbital theory, we can figure out what are the atomic orbitals involved to make the chemical bonds and determine the hybrid orbitals or the kind of bond being made. Okay, so with that, I will finish for today. And then on Thursday, we will talk about intermolecular interactions and probably a little bit about colligative properties. Okay, so we will figure out how the compounds are held together. So with that being said, thank you very much, and I will see you on Thursday.